Recall the series summation 1 by n power p, n going from 1 to infinity, diverges if p is less than or equal to 1, and converges if p is greater than 1. Now observe this function 1 by n power p. I can consider it as 1 by x power p, and the function is now defined on 1 infinity. Okay, I can extend 1 by n power p to the whole real numbers in 1 to infinity, right? Now it is natural to study whether by using this function 1 by x power p, whether we can conclude something about the series summation 1 by n power p. And that's precisely what the integral test tries to tell us. It sort of says that the sum of the series is related to the area of this extended function between n and n plus 1. Okay, so these vague remarks will now be made precise in this theorem. This is the integral test, and this is a very powerful general test for convergence. Let f be a continuous function defined on close 0 open infinity. Okay, further assume that f is positive and decreasing. Okay, then summation fn converges if and only if limit n going to infinity of integral 1 to n f exists. Or in other words, the series summation fn converges if and only if the improper integral exists, and I must add to be precise, and is finite. Remember, when we defined the improper integral, we did allow the possibility that the integral could be plus or minus infinity. We don't want that. That is obvious. Let's see a proof, and my vague remarks about the area between n and n plus 1 and the value of the series being related will become clear in the proof. Okay, so proof. Set an by definition to be just this f of n. Okay, and set bn to be integral n to n plus 1 of f of n. Okay, now we are assuming that f is decreasing, which just means that f of n plus 1 is less than or equal to f of n. That's what decreasing will imply. Okay, also it actually says that if x is there in n plus 1, then f of n plus 1 is less than or equal to f of x is less than or equal to f of n. Right, that's what decreasing means. Okay, in other words, if I integrate from n to n plus 1 this set of inequalities, what I would get is f of n plus 1 is less than or equal to integral n to n plus 1 f of x is less than or equal to f of n, obviously. Integrating the entire equation from n to n plus 1. That just means that the area of the function, or area of the region under the graph of the function from n to n plus 1 is dominated by f of 1, and it dominates f of n. Sorry, it's dominated by f of n and dominates f of n plus 1. Okay, now what I can do with this is translate it in terms of ans and bns. So what we get is 0 is less than an plus 1 is less than or equal to bn is less than or equal to an. Okay, so Bn is sandwiched in between an plus 1 and an. Okay, now a simple application of the comparison test. You have to apply it twice, once for each inequality, an plus 1 less than or equal to Bn and Bn less than or equal to An. We get summation An converges if and only if summation Bn converges. This just follows immediately if you apply the comparison test twice to the inequality that we have. Okay, but what are summation Bn? Summation Bn is nothing but integral 1 to n of f, right? Summation, not summation Bn, the summation n equals 1, or rather let me be 100% precise, summation k equals 1 to n bk is nothing but integral 1 to n f, which means summation Bn or summation bk converges if and only if integral 1 to infinity f exists and is finite. In other words, the convergence of the series an is determined by whether the integral 1 to infinity, the improper integral of f from 1 to infinity, converges or diverges. So the proof is rather simple and uses the simple idea that the graph, the area under the graph, is related to the terms of the series. Now, using the integral test, we can easily show that summation 1 by n power p does converge if p is greater than 1. Let's see how this is done. So example, consider summation 1 by n power p. Now choose f of x equal to 1 by x power p. Okay, and p, let's first take p greater than 1 and see what happens. Then integral 1 to n 1 by x power p is nothing but 1 by 1 minus p n power 1 minus p minus 1. Okay, in fact, for this we don't need to assume p greater than 1, we just need to assume that p is not equal to 1. When p is equal to 1, what I have written is not correct. Integral of 1 by x is actually log x and not the formula that I have written. Now, as n approaches infinity, the above quantity is finite if p is greater than 1, and infinite if p is less than 1. Okay, that immediately gives that when p is greater than 1, the series converges by the integral test, and when p is less than 1, we immediately get that the series diverges. Of course, for the p equal to 1 case, we have to do a special argument which we have already done in an earlier chapter to show that the series summation 1 by n diverges. So we were able to show that summation 1 by n power p, except the p equal to 1 case, whether it converges or diverges, we were able to show it pretty easily using the integral test. Okay, so can you show using the integral test that summation 1 by n diverges? Yes, you can, and that's going to be left as an exercise. Use integral test to deal with 1 by n also. Deal with summation 1 by n. So this concludes this module. This is a course on real analysis, and you have just watched the module on the integral test.